All right. Good morning, those of you who made it in. Yeah, it's 8:35. This is COMP2404, Introduction to Software Engineering. I'm Daryl Hill, your instructor. So assignment 1 is due. We're here on the 30th, I guess. We're a little bit, we're not quite lined up with what I have written here for the subjects, but I kind of restructured the beginning, and I think it worked out better, even though there's a bit of repetition. Regardless, today we will be looking at memory management in more detail, and then this other stuff we'll catch up on at some point. Tutorial 3 is due tomorrow, and did this just freeze on me? I can't seem to change pages anymore. Just a second. It's very typical for Microsoft, I find, is that everything works great until it crashes. Of course, I do sort of run a lot of things at once, but okay. Perfect. Okay, so assignment 1 is due on Sunday. So no late assignments. Make sure you submit whatever you have. If you don't get finished, hopefully you get finished. And I'll release assignment 2 and the next tutorial this weekend, most likely. I just want to take one more look at them. Try and eliminate any possible sources of errors. Yeah. So a couple of things. Tutorial 5. I'm going to change a few due dates here coming up. So this is your 2 weeks notice. My goodness. So tutorial 5 is officially due on Friday at midnight, because I can't make anything due on the weekend surrounding the reading week. I'm not going to mark it until Sunday, but yeah. And assignment 2 is officially due on Monday at midnight, right? Again, I can't make it due on the Sunday. It's against the university policy, so it's due on the Monday. It still gives you plenty of time to finish it. All right. So yeah, any questions on the calendar, the schedule? How's assignment 1 coming? Easy? Hard? Is it, how do you find the tests? Like, are they useful?
One thing where I'm not too sure if it's doing it correctly, because I remember like the last class, you were mentioning how you might not get all the points if you don't like add order.
Yeah.
But it's still like when I tested it, like I did like test all, and it gave me like all of my marks. So I don't know.
Well, yeah, again, so if that's hilarious. If it's not testing properly, that might not be the mark that you get, right? You're still going to get, if there's marks for adding things in order and the test script messes up, then we'll still deduct those marks. So yeah, try and get it working. The test script is a guide, and yeah, there might be bugs in it. Almost certainly there's bugs in it. Yeah. All right. Other comments or stories or anything?
I've got one, but I'll probably save it for the end because it's kind of long.
Okay. All right. I mean, you can write your own tests too if you don't find those that are working for you. The idea was for the TAs to use it as sort of a guide for their marking, but yeah, I'll have to watch out for bugs. Okay, so last class we were talking about memory management, so we're going to continue that today. In particular, we were talking about, let's go to, okay, we were, yeah, example 3. So we were talking about dynamic memory and static memory, which are things that we've talked about quite a few times at this point. But essentially, right, if we look at the memory model, I have my main method, and that goes in a stack frame. And then I declare a local variable that is an int pointer, right? And that is stored with my stack frame. And then when I call, if I have a line of code saying equals new int, well, then the compiler goes over to the heap, finds 4 bytes, and allocates an integer here, and returns the memory address to this pointer now. All right, so that is allocating dynamic memory. Now the pointer itself is still a local variable, and it's in some sense statically allocated, which means that if my calling function goes out of scope, that variable is deleted for me, which can cause problems, but you know, maybe not so much in the main function. Once the main exits, your program's done, so all memory gets released. But in general, if I say new int somewhere, then I probably want to also delete that pointer. And when I delete the pointer, it doesn't actually erase the memory, although, I mean, who knows? I'm not sure exactly what the compiler does. All I know is that that memory is free to be overwritten by something else. And what the compiler does exactly probably depends on what version you have, what compiler you have, etc. So yeah, it just stops tracking this piece of memory, and now something else might overwrite it. After I delete that pointer, I can still use it. I mean, I might even get away with it, but it's not a good idea because at some point that memory will likely become corrupt. The other thing, the other part of this example that we didn't look at, we didn't get to before the end of class, but let's say, I'm going to make this a little bit bigger so I have more room. So I have my main function, and now I declare, up till now, we've only statically allocated arrays, but I can dynamically allocate an array as well. So I can say, for instance, int pointer array equals new int, and then I'll put perhaps of size 4. All right, so what happens at that point? Again, that's a call to new, so the compiler goes into the heap, allocates an array there of size 4, and then it returns the address of the first location back to this pointer. So yeah, up till now, we've only been statically allocating arrays. Now we're going to be talking a little bit about how we can dynamically allocate them as well. And that gives a rise to a whole bunch of extra complexity, because now we can dynamically allocate an array of, in this case, primitives. So I can dynamically allocate an array of integers. I can also dynamically allocate an array of integer pointers. I can dynamically allocate an array of object pointers as well. So we're going to take a closer look at all of those things later this class. But for now, if we go back to the example. Okay, so here just in main, we've declared some pointers, and we've assigned them some values and then deleted them. But I can also dynamically allocate an array, and this array goes on the heap. And it's an array of ints, right? If I wanted an array of int pointers, it would look something like this. But I don't. I want just an array of primitives, and then I can access it. So I assigned it to a pointer, So if I statically allocate an array, it looks like this, right? It looks, what does it look like? Int array 5. Right, so in this case, I've made a new variable called ARR, and I've assigned it the address of this statically allocated array. So this array is on the stack, and this is actually, even though it's hidden, this is actually a pointer, right? So what I'm doing in this call, I'm statically allocating an array on the stack. Here I'm dynamically allocating an array on the heap. But the syntax for both of them is the same. So let's call this P2. For some reason, I have P3 here. And let's make it the same size. So everything that I do with P3, I can do with P2 as well. All right, so they're both arrays of integers. So the syntax is different when I instantiate them, when I allocate them, but when I use them, the syntax is exactly the same. There's no difference. And I can, I can declare another pointer and have that point to either of these things. So an array, whether it's on the stack or on the heap, requires a pointer to point to it. Okay, so however, yeah. So we can assign them values, and then we can print out those values. Yeah, let's actually just do a whole new one. So yeah, these are dynamically allocated. And these are statically allocated. All right. Okay. So dynamically allocated, statically allocated, whether it's on the heap or the stack, the array, how I interact with it, the syntax is exactly the same. All right. I guess the one problem I have now, though, is if I run this with valgrind, besides the fact that I forgot an inline there, is, I haven't deleted my array. So it says I lost 16 bytes in one block. So that is, each integer is 4 bytes. So yeah, that's an array of 4 ints. And one block means they're all contiguous. So in order to manage that, if I want to delete an array, I use the delete, but I give it a special signal to the compiler to say, I know this is a pointer, but it's an array, right? So you're going to go and you're going to deallocate or erase that entire array rather than just the one location. All right, and that becomes a little more significant when we get to objects, because it means that the compiler is going to call, if it's an array of objects, it's going to go call the destructor on each of those, rather than simply the first one. If you did this, that might work. I don't know. Sometimes it crashes, sometimes it works. Probably depends on the compiler again. But yeah, mileage may vary. To delete an array, you use this. Oops, that's not what I wanted. Okay, so now it tells me that all heap blocks were freed. You know what? Let's try it and see what happens here. Oops. Valgrind. So it did work in this case. All right. We'll try it again when we look at objects, but yeah, I've had it crash. I've had it. I guess it's complaining, eh? Yeah, mismatch free. it's complaining. So the compiler did its job and it freed everything, but not without asking some serious questions about what we were doing. All right. Questions on that? Okay. Okay, so we've been talking about memory leaks a little bit. So now we're going to look at them in a little more detail. So C and C++ do not provide garbage collection. I was going to say they don't provide reference counting, but C++ now does. Of course, it has smart pointers and things like that. But in general, it means we can have memory leaks. So what is a memory leak? It's a block of dynamically allocated memory where I've lost the pointer, right? So it's something's on the heap. I have some pointer in local memory somewhere that, or anywhere. I mean, it could be in the heap as well. But I have some way to get to that piece of memory from my code. It is possible, however, to lose it. And then what happens is that the heap makes sure that nothing else gets allocated there, or the compiler makes sure that nothing else gets allocated there. But of course, I don't have a reference. I can't use it. I can't ever delete it. So it's useless memory now. It's called a memory leak. What causes them? Of course, if you forget to delete something, that's one cause. But I think, once you learn how to manage your memory, then that's sort of less common. What's more common is that, I guess you forget to delete it at the proper time. So your pointer gets clobbered, right? So I have a pointer, I assign it a piece of dynamic memory, and then I point it at something else. Well, I've lost the reference to that memory. Or a pointer moves out of scope, right? So if I declare one inside a function and I say equals new int, and then I exit that function before I call delete, that memory is gone. That pointer is clobbered. So why are they a problem? We talked about you can lose access to data. It's permanently lost, right? You can't ever really find that. Also, there's a finite amount of heap space given to a program. So what happens is that, basically code repeats. All your code repeats. It's industrial grade software is running for months or years. So a piece of code that, leaks a piece of memory, well, every time I call it, I have a new, I call it, I make an array of ints on the heap, and then I exit, I lose that pointer, I come back to it, I make another array of ints, I forget, I lose it, I come back. So the heap is saying, well, okay, this is memory that I need to keep, so nothing else can get allocated there, but I've lost references to it, and eventually your heap fills up, and your program crashes. Maybe that's what happens with my drawboard, I'm not sure. All right, so yeah, in this example, we're just going to show a couple examples of memory leaks. So memory leak number one, in main, I call this memory leak function. And if I go down here, all it does is it declares a local variable and then assigns it a new integer on the heap. And then maybe I do some operations with it, and then I return without deleting it. Of course, that causes a memory leak. All right, so it allocated a new integer. It, did an operation. But of course, that memory is lost. Definitely lost 4 bytes in one block. It's not even, sometimes at the end of your program, it'll say still reachable, but this is definitely lost because I lost that reference. Memory leak number two. Right? Maybe I make a new int and I pass it in, or maybe I'm not using this properly. I'm passing in an integer. that maybe I want to do something with, but somewhere in my code, I stomp on that. Or no, not stomp on it. I pass in that address. I still have a reference to the old address in main, but again, what I've done here is I've allocated a new memory location. I've used it, and then I've returned, you know, I guess the idea here might be that you think you're returning a value, but you're not. You have to pass in, just passing in a pointer, and then stomping on that pointer does not return that value. So let's see here. So yeah, again, I definitely lost this time 8 bytes because I forgot to delete this one. I could delete this. Yeah, okay, so I lost 4 bytes in memory leak number 2. Yeah, so I mean, nothing super groundbreaking about all this, but the other thing I can do is just directly stomp on a piece of memory. So I'll say, I'll make a new pointer P1 and I'll assign it a new int. And then at some point I assign it to some other value, some other value. And then I've lost that original pointer forever. So even though I called delete on P1, I've stomped on that memory and it's gone. Yeah, so definitely lost 4 bytes. That's the clobbering a pointer. All right. Oh yeah. So yeah, if I wanted to, we'll come back to this when we look at double pointers. Anyway, I think it's relatively straightforward stuff, but is there any questions? Okay. Okay, so how do we prevent memory leaks? We always explicitly deallocate the memory. So every time you write new, you should have a plan for writing delete. It should be, often they're in the same function or in the same class, but not always. But it's a pretty good rule of thumb. So yeah, where am I going to delete something when I make it? You know, if you come from a language like Java, of course, Java handles all that for you. You can still have memory leaks in Java though, so it is important to understand this stuff. Because Java does reference counting, and you can actually, you can have a dangling reference somewhere that to some memory that you never use. Anyway, you can mess things up if you really try. I've done it. So a good rule of thumb, objects are deleted where they are created. Occasionally though, we create objects in one place and then we hand them off to somebody else, right? So an example of that would be a factory design pattern. I'm going to make a new instance of an object and give it to you. So it's made in my factory class, but I don't delete it there. So that, yeah, it's a bit of an advanced design, but we're actually going to see factory design pattern in this class. So every dynamically allocated object must be deleted in exactly one place. If in doubt, if you think you might delete it in more than one place, after you delete it, assign it null. So you can delete a null variable and that'll be fine. But yeah, so we often delete it in the containing object, not so much data structures, eh? So when I add things to a data structure, I should not really be deleting them, because the data structure has a different responsibility. It's simply managing that data, but the responsibility for deleting it should be in whatever contains the data structure. We'll talk about that. Containers often form a hierarchy of deletion responsibilities. Yeah, so we talked a little bit about assignment 1 and how it's structured, right? So we have our main game trucks, and then this contains a lot of other trucks. And then these trucks contain a bunch of reservations. So the hierarchy here is that the trucks should delete the reservations and the game truck should delete the trucks. right? So if you do that, then all your memory will be properly managed. You will most likely not have memory leaks. Although, of course, you know, anything is possible, but. So yeah, hierarchy of deletion responsibility. Often our apps, at least in this class, appear as a hierarchy or a tree. And that tree is often the, you know, how we decide what gets deleted by what. Also, make sure you don't clobber a pointer. Yeah, so a lot of these come down. I don't know if you guys have heard of Rust. So Rust, it's supposed to be fast like C++, but they attempt to make sure that you don't have memory leaks. So they have things like responsibility. So you have a primary pointer. And if I pass that somewhere, I pass the responsibility for deleting it to wherever I'm passing it. And if I don't want to delete it there, then I should pass it back. Because once a pointer goes out of scope, it just automatically deletes whatever's there. So those ideas are sort of what you should be doing in C++, is that, yeah, you should consider, maybe I have multiple pointers to the same memory location, but there's one that is the main one that is responsible for deleting it. And that should be ideally done after all of the other references expire. Anyway, yeah, so no reference counting in this class, no garbage collection. You kind of have to plan ahead. And yeah, the thing about garbage collection and reference counting is that if the deletion happens at the wrong time and it's a game, for instance, you want to delete in the middle of the game because you're going to get a slowdown. You're going to get a lag. So all memory access should happen outside of these times. So even if you're using smart pointers and reference counting and things like that, you still have to be aware of when those things are deleted if you want to write good code, whether or not it's in C++. In Java, you have to do the same thing. All right. So, yeah, we've talked about this. Always use new, don't use malloc, because new calls the object constructor. Yeah, which does all the, you know, fun stuff like member variable initialization. And always use delete, because delete calls the destructor, right? So that makes sure that all my memory is managed properly. Resources is cleaned up, and memory is released. So P4. So our calendar class here that we wrote last class, so we had a date class that we put in our calendar. We could add and remove dates from our calendar, and they added in order, and we removed them. We closed the gaps in the arrays. What we didn't do, however, is clean up our memory, right? So in my add date function of my calendar class, I pass in information to make a new date, and then in add date, I call new. So because I'm doing this in the privacy, this is hidden away from outside use. I don't make objects and pass them in. I make the objects inside my class. So most likely, due to encapsulation and whatnot, I probably want to delete this, right? Nobody else has a reference to this date. Only I do. So if I don't delete it, nobody's going to. So yeah, so the hierarchy of responsibility here is, even though this is very simple, is the date, of course, does not have any dynamic memory, so they don't have to delete anything. So I don't really need a destructor, although, you know, we have one just to announce that we're in the destructor. But the calendar here is responsible for deleting those dates, right? And I decide that as the programmer. And basically the reason is because nobody else is going to do it. So actually, what is that, P4? We'll run it first. Yeah, I didn't return true at some point. Okay, so everything works fine. Valgrind. Yeah, I lost 24 bytes in 2 blocks. So 5 allocs, 3 frees. So when I deleted them, I think when I removed them, I deleted them. But then when my calendar goes out of scope, it doesn't get deleted. And actually, let's do this. Okay, so I have a no argument constructor, so that's fine. It's going to complain here, but I don't have the proper arrow operator. There's a way to do all of them at once, but I never remember what that is. It's like Control-Alt-L or something. Okay, so now I have a new calendar. Yeah, okay. So obviously I'm going to have a memory leak. I had a memory leak before when it was statically allocated, but for sure I'll have a memory leak here because I didn't delete it. But if we go now into our destructor, now we can delete any dates that are left over. I is less than, I believe we called it num dates, yeah. So I'm just going to go through, and for every valid date, I'm just going to delete it. Okay. And if I look at here, this is a statically allocated array, so the array itself will get deleted for me. If I made a dynamically allocated array, I would also have to delete that. And this is statically allocated, so I don't have to delete it. So at this point, I've deleted all my dates. I still have one major problem because I changed my code a little. Is that I have to delete my calendar. So in the hierarchy of responsibility, my calendar is responsible for deleting the dates, but I am responsible for deleting the calendar, or my main function is. So here I have to, once I'm done, I will delete. And then that will trigger the destructor, which will trigger the destruction of all the dates. Okay, yeah, so all heap blocks are freed, no leaks are possible. And all I had to remember was to delete this memory, right? So the calendar handles all the dates. Whether I remove it, it deletes it there, or if I delete my calendar, then all the remaining dates are destroyed. So yeah, if you plan it out so that you have that proper hierarchy, then memory management is easy. I delete my one thing that I used, and everything else just kind of collapses like dominoes. All right, questions? Yeah, easy stuff, eh? Okay, so yeah, returning objects by reference. So there are times where I do want to make a new item, something that's allocated on the heap, or perhaps something that already exists. I want to pass back that pointer. I've shown you the syntax, but we're going to talk a little bit about, what exactly is happening in terms of memory. So I want to return a pointer to some dynamic memory from a function. And essentially, I want to pass in the pointer by reference. We've talked about how to pass something by reference. You can pass it by pointer, or you can pass it by reference. I'm using reference here, there's two meanings. The one is the reference, and then by reference in general means I'm passing it by the memory location. Okay, so here I have a double pointer. This is a sort of a memory map, similar to what I did before. So let's say I statically declare an int, named I, is type of integer. Its value we'll say is 42. And its location is A8. So these are the hexadecimal memory locations. Then I declare an I pointer, right? It is named I pointer as type pointer to an int. The value Well, maybe I say int I pointer equals the address of I. Okay, so then the value is I take I return the address, which is A8. And its location is AC. So now if I declare a double pointer, we call that dptr. Its type is, it's a pointer to a pointer. It's a pointer to an integer pointer. Memory location is B3. And when I allocate it, maybe I say it's equal to the address of, this thing's getting in my way, I pointer. All right. So I'll say D pointer equals address of I pointer. All right, so if I wanted to allocate these things directly, I would go, yeah, I could do it like this instead of passing it by reference to a function. So I declare this double pointer and I assign it the address of I pointer, which is AC. Sorry. Yeah, I got these mixed up. AC and B3. Okay, so now if I wanted to do something like access my integer value from my double pointer, I can do a double dereferencing. So cout, I'll dereference D pointer twice. So what does that do? I go to D pointer. The first dereference says, you know, take this value and go to that memory location. So okay, we go to the location AC, and then I dereference it again because it's a pointer, and it says, okay, take this value and go to that memory location. So then the compiler looks here and says, I have a value of 42, so that's what I print out. All right, so it's a double pointer is, you know, technically not that much different from a pointer. I can't declare a double pointer directly and then assign it address of I, right? That's meaningless. Yeah, I only have one address for that. So I have to have, if I'm using a double pointer, I have to have this intermediate pointer. And if I use a triple pointer, I have to have an intermediate double pointer and an intermediate single pointer. I can't just declare this on its own and expect it to work. So yeah, we'll look at an example of that shortly, but questions? Okay. Well, here is, yeah. The syntax for double pointers in case you need a reference guide. So if I want to return a date using a getDate function, I'm passing in a date pointer by reference. I can actually change that to actually accept a reference as well, which I'm not sure why they don't do more often, but or maybe they do, and I'm just out of the, you know, I'm not in those circles, but yeah. I've never seen a pointer passed by reference. I've only ever seen double pointers, but maybe they use it. I don't know. However, so yeah, to call this getDate function where I'm passing a pointer by reference, I pass in the address of my pointer. And then when I'm using my double pointer D, I have to dereference it once to get back to the pointer, right? So date2 is a pointer that has this address, and I want my pointer to have the same address. I think, yeah, let's look at this example from here. So yeah, if I can remember. Date D1 is declared. Yeah, so I have date 1. It's a type of date pointer. I'm just going to call it D star. It has a value of, let's see. When I declare it, it has no value. So we'll just say null. And its location is A4. Date 2 is also a pointer. And here I assign it to this new date that's on the heap. So that's this date here. and it's at location DC. So its value is DC, its location is AC. And then I declare that double pointer, it's a parameter. It lives at location, so we call it D. It's a type double pointer. And its location is B3, and its value is initially null, but yeah, I dereference it and I assign that value to, oh no, sorry. Its value is the address of date 1. So let's go back. Date 1, A4. So I passed in this double pointer, I passed in the address of my single pointer. So now when I dereference it, the compiler says, okay, I'm dereferencing to this memory location, so I'm going to go here. I dereference it and assign the value from date 2. So I go here, and in this value, I assign the value of date 2, which is DC. All right, so that means the original pointer that I passed in, date 1, gets that value of the dynamic memory that I wanted, DC. Right, so that's in all of painstaking detail how the double pointer works. Yeah. Questions? Okay, so if we look at our example, just for fun, just for completeness, we did that with our calendar class. We had a get date function that takes a double pointer. And then in my main function, when I wanted to get something, I declare a pointer, a single pointer, and then I pass in the address of that single pointer. And then we saw how when we reference it, we get back actually this single pointer, and then we can assign it, we can assign this pointer to some address that I get from in here. All right, so yeah, I can, let's say, out. No, so getting the dates using the double pointers, I got these dates. Do I have two the same? Yeah, I think oh, I removed a date. So my guess, maybe I forgot to, I probably forgot to do bounds checking in the function. No. Oh, you know what? It returned false. I just didn't do any error checking. So I got, yeah. When I printed out this didn't change the value of my double pointer, my D pointer, my date pointer, sorry. So I just printed out the same thing twice, but yeah. Questions? Yep. Yeah. Yeah, so it points to the memory address of the, so I have a pointer outside that I want to change where it points. So yeah, I have a pointer to that pointer. If I dereference it, now I have access to this memory location from outside of my function, and I can point that to wherever I want. Yeah, just for fun, let's do, I can pass a pointer by reference. This might simply be confusing, but the principle is the same, except how the compiler handles it is different. So now this is, I'm passing in a pointer by reference. This is a single pointer, so I would just assign it this value. And where's my other mistake? So I think syntactically this is actually easier, but again, I don't see that used very much. And now when I pass it in, I don't need to pass in the address. The compiler's handling that for me, right? So I can pass in, we passed in objects by reference, integers by reference. You can pass in pointers by reference as well. And syntactically, everything makes a lot more sense. You don't have to dereference it, but I've never seen it used. But it does work. All right. Okay. Lastly, we will talk about dynamically allocated arrays. We've talked a little bit about them. We've seen how we could dynamically allocate an array of integers, but there's lots of repercussions when it comes to objects. So dynamically allocating an array, we use the new operator with the square brackets. Again, if we make an array of objects, even though it goes on the heap, the same thing applies. I call the default constructor on each one of those objects. And if it doesn't exist, you get an error. So we can deallocate them with the delete square bracket operator. And if it is an array of objects, then the destructor is called for every element on that array. So that is how, again, there's that hierarchy of responsibility where if we call this, then that array is responsible, or the compiler is responsible for calling delete on each of those objects contained within the array. If you use delete without the brackets, I don't know, man. Try it and see what happens. So yeah, arrays have two types of memory allocation, static and dynamic. And arrays can store objects or object pointers, right? So we saw ints, now we're gonna look at, I think, dates again. So we have 4 ways of storing data in arrays, and each has some subtle differences in syntax. And actually your next tutorial has you do operations on all 4 types. But yeah, so again, we have our date class, nothing special. We do have a default constructor. So if we make a statically an array of objects, the default constructor will be called. Yeah, nothing else special, less than, I guess, but. And we make note of every time we call a constructor or destructor. And then in our main, we have 4 functions. So we have statically allocated, each of them has a different array type, and they all store dates, but in different ways. So the first one, statically allocated array of objects. The second is a dynamically allocated array of objects, static pointers and dynamic pointers. So let's take a look. Oh yes. I guess, default example here is simply, so when we mentioned earlier about how every time I have an array, whether it's on the stack or on the heap, it's technically that variable is a pointer, right? Even though I'm using a different syntax, it is a pointer. So I can actually make a new date on the heap, a single date, not an array, and I can dereference it using this array syntax. Probably not recommended, but can be done. Would definitely cause confusion for anybody looking at your code. But yeah, I can make a new date, and I can print it out using, instead of dereferencing it or using the arrow operator, I can use this. This tells the compiler, go to this memory location, and 0 hops over from that memory location. So that happens to be a date. So yeah, all right, let's get rid of that, and let's look at statically allocated objects. So I am going to statically allocate an array of date objects. I believe we've seen this before, and max array, what is it? Max size is 2. So it's just an array of 2 dates. And the default constructor will be called on each of them. And then if I print it out, I print it again. Even though I didn't declare it as a pointer, technically this is just a pointer. So, and And in some sense, this is a dereferencing operation. Let's do. So yeah, we'll just statically allocate an array of date objects and then print it out. That's it. So each of them gets the default constructor. We can tell by the year, which is 1901. And then it prints them out. And then when we exit, everything gets destroyed for us. So we statically allocated that array. The array gets deleted for us, and delete is called on each of the date objects. I did not call delete deliberately on anything. So everything is statically allocated. Memory management is done for me. Yeah. The other thing I can do is, as mentioned, this is simply a pointer. I can create another pointer and point it at the same address and then print out the same array from that pointer. So there's nothing special. If I want two references to an array, they're both just pointers. So yeah, so printing the array again using a pointer, and that works just fine. All right, questions? Okay. And yeah, these, I guess, I can dereference again simply by using these, the square brackets. I wonder if I could do this. Let's see if that works. Yeah, so that works fine. So again, they're just pointers. I can dereference them using the arrow operator or by using the square brackets. Yeah. Okay, so statically allocated array of objects. Let's look at dynamically allocated array of objects. So again, the syntax here, now it's a little more explicit that it's a pointer. I can't declare it using the square brackets directly because that's static. So I say new, the type, and then the square brackets indicate that the compiler should allocate an array of that type. Okay, so this is a dynamically allocated array of date objects. When I access them, the syntax is exactly the same as a statically allocated array of date objects, right? I can dereference them using these square brackets, and then that returns an object, so I use the dot operator. And then I can print them all out, and then delete the array at the end. So we'll leave that for now, but we'll come back to that. So dynamically allocated. Now I have these in a different order, I guess. But bad allocation. Cool. Yeah. Dynamically allocated array of objects. Oh. Max size is 2. So for some reason, I think I had it set to 3 at some point. So yeah, I tried to access some bad memory, and the runtime system caught me. Let's try that. Okay, so dynamically allocated array of date objects. Again, when I call new on that, the constructor is called on both of those locations. So it goes to the heap, it makes a new, let's take a look at that. So I call from main, I call a new date, and then 2. So the compiler goes to the heap, makes an array, returns that pointer, and calls the constructor on 2 date objects. All right, so that's a dynamically allocated array of objects. And yeah, So I set the dates using the set function, the dereference, I print them out, that works, I exit the function. The destructor is never called. And the reason is because even though they're statically allocated dates, I did not delete the containing structure, which in this case was the array. And once I delete the array, then the destructor should be called for me. Okay, so yes. The constructors, the default constructors are called. I set some values, I print them out. And then when I delete the array, the destructors are called. But I do have to delete my dynamically allocated array in order for that to happen. Questions? All right. What's next? Static pointers. So a statically allocated array of pointers. You've seen this. This is actually what you're supposed to do on your assignment. I don't know what I did here. So again, to statically allocate an array is the variable name followed by the square brackets with the size inside. And preceding that is the type. So date pointer is the type. Now, technically, all right, well, we'll get into the ins and outs of that. So this is an array of pointers, so I can take a pointer and I can assign that to one of the memory locations, or I can directly call new and assign that to the other of the memory locations. And then I can print them out. So let's do that, static pointers. Okay. So yeah, these get called not with the default constructor, but only when I call new. So you can tell by the year because it's not the default year. I've actually assigned these values when I created them. And then deallocating array one element. Yeah, and then I deleted them and then I exited the function. Did I delete them? Oh yes, I did. I missed that part. So I did delete them at the end. And that's when the destructors were called and then we exited the function. Yeah, so simple stuff. Worth noting that this array one is actually a double pointer. Right, so it's and why is it a double pointer? So I called, yeah. Here, let's do this. So I have my main function and I made an array of date pointers. All right. Or did I? For time. All right, so I have my, not my main function, but whatever function this was. I statically allocate an array of date pointers. But of course, all arrays are simply pointers. So if I want to, yeah, I need a double pointer to point to that because I'm pointing, this is the, I'm pointing to a pointer basically. So I need a double pointer here, even though the syntax is I declared it as a single pointer when I did this. This is actually a double pointer. So if I dereference it twice, I go here, and then I go to wherever this is on the heap somewhere. So yeah, and then to sort of illustrate that, I declare a double pointer, and I assign it to my array. And then I can use my double pointer exactly the same Exactly the same way as I use the variable for the array. All right, so printing from a double pointer prints exactly the same way as printing from the original array. So technically, this is just this ARR1 is simply a double pointer. It's declared a little bit differently, but yeah. And then I have to delete both of those things. I don't have to delete the array because I declared it statically. The array gets deleted for me. All right. Questions? One more. One more on this exciting tour of arrays. So dynamically allocated arrays of pointers. And we've been statically allocating arrays, but this actually is probably what you would use most often in the real world, because you want all of that memory to be on the heap. And you want to use pointers so that you're not allocating objects unnecessarily. So dynamic pointers means that, well, if we look at our diagram here, in my function, whatever it happens to be called, and let's say this is the heap, I'm going to say, date double pointer array equals new. I'm going to put this over multiple lines. So the type is date pointer, and then this tells the compiler to make an array, or tells the runtime system to make an array of date pointers. So what this does, we go on the heap, and then I make two date pointers, and this address is passed back to this variable. Can it crash again? All right. Yeah, all right. I think I'm going to stop drawing with drawboard. And then if I want to, so I've assigned I've made a array of pointers on the heap. And then from there, I can allocate new dates to those locations. All right, so here I've declared a double array. Even if I did this all in one step, I did it in two steps, but if I did this, I still have to declare it as a double pointer, right? And I could use this double pointer to point at a statically allocated array of pointers, just the same. So this step goes to the heap, makes that array. Then I can make some new dates either through a pointer and then assign that pointer to one of the memory locations of the array, or I can assign a new date directly. So both of those dates live on the heap. And then I have, Jesus, I don't dare open that again. But I have, of course, my function with my double pointer. It's pointing to the heap where I have date pointers, and then I have two dates elsewhere on the heap. These are objects. So this pointer points to the first location of this array. This location points there, that location points there. So I can actually double dereference this and get to the first one if I wanted to. Or, typically what I would do is say, all right, so that's going to return this pointer, and then I can use the arrow operator to call print, for instance. So yeah, this is by far the safest way to assign memory, because the bulk of it is all going to be on the heap, where I have more room. If I store all that stuff on the stack, I could run into a Stack Overflow problem. However, I do have to manually delete everything in this case. So I have to call delete on each of these individually, and then delete this array. If I delete the array first, that might still work, maybe, but you could get corruption here before you call delete on those dates. So yeah, delete the elements first, like I do here, and then delete the array itself. Yeah, so you can see both dates are destroyed. End of program. Yeah, let's for fun see if this works. If I move this around. So because I called these directly afterwards, it's possible that memory location is still valid, but maybe not. There's no guarantees. Yeah, I got a segmentation fault. All right, so yeah, as soon as I deleted this, this data became corrupt. So yeah, always delete the data first and then the array itself. All right, questions? A lot of technical nonsense for a Friday morning, but yeah, it is necessary to sort of understand all these different cases. Okay. All right, so a quick reference guide if you are in doubt about what syntax to use when you're asked for some sort of array, you can always kind of refer to these slides and take a look at the syntax. Yeah, all right. So that's it for arrays. Now we're going to, we talked about, of course, all the, the small technical details of C++, and not only C++, but programming in general. We've talked about, going from imperative to object-oriented programming. So how we sort of organize our code a little better by collecting it into classes where we have data that's related, and then functions that act on that data. And then we talked about constructors and destructors. So how those, how now that we have objects, we probably want to have a function for initializing and for uninitializing. And then we talked about memory management and the impact of all these decisions we made so far on the fact that we have to manage our own memory. So yeah, we've covered basically at this point a lot of technical ground. So now we can get into some higher level ideas. So to start this next section, we're going to talk about object-oriented software engineering in general, which means that we're going to be talking about some high-level software engineering techniques as it relates to object-oriented software engineering. So we'll talk about what is software engineering, which we've mentioned a few times already. Some of this is repetitive. I really have to prune these slides a little bit. We'll start by talking about low-level design. So when we're, building our entity objects, which we're going to talk about, what are sort of the things that should be guiding our decisions? So how should we think about them? And yeah, so we'll talk about encapsulation, which is basically where I protect everything in my objects. That is sort of related to the principle of least privilege. The principle of least privilege, when I apply that, leads to an encapsulated object. And we'll talk about why that's important. We'll talk about abstraction. So I want interfaces to my object to be simple. So abstraction means that I'm taking away all the technical details and just saying, I'm making it easy to use, right? And I'll handle all the technical choices. You'll see that abstraction solves a lot of problems generally. We'll talk about high-level design. So when I'm starting, what sort of workflow, in the beginning, like what do I do how do I think about the design of my application, what the workflow is, how to refactor, we're going to talk about. We'll get to examples of that later. And design categories, which is sort of a more concrete way to help organize your application. We'll talk a little bit about testing. I do want to put more testing in this course, but for now we're stuck with this. We'll talk about what types of testing these are, and a lot of these are, so the unit testing is in some sense, as we go on, more and more this becomes your tutorials, our unit tests, and then integration testing is sort of the tests that we, like your assignment 1 test, would be closer to integration testing, and then systems testing would be if we had a finished product, then we can start integrating it with outside systems that they're supposed to communicate with and make sure that things work there. But we'll talk about all that later. All right, so what is software engineering? In general, it's a set of best practices, strategies, and design patterns used to deliver high quality software. It's not, so when you engineer a bridge, for instance, there's a lot of rules, of course, because, well, if you don't follow certain rules of physics and things like that, your bridge is going to collapse. There's a lot of important considerations in software engineering. There's a lot of important rules to follow, but in general, it's a lot more creative than designing a bridge. Problem solving in software engineering, you don't generally have a blueprint. Well, sometimes you do, but if you're creating a new application, you don't, right? You're going to have to figure stuff out as you go. So it is a little bit different from other types of engineering. What is high quality software? Code that's reliable, easily, so not drawboard, easily modifiable, extendable, right? So I can add new features to it. Generally speaking, all software is updated. Everything on your phone gets updated regularly. So what parts are updated, what parts will change, often influences your design decisions, right? So different design patterns are better for different types of change. We want code that's reusable. It's nice. There's a lot of libraries that we use. So, if we solve a problem and we think of a sort of an optimal solution, or we're getting very good at it, maybe, you want to package it into a library that other people can use. So you want to think about other people using your software as you make it. Scalable. So it's harder than you'd think. So that means, does my program work for 10 people? Yes, hooray. Does it work for 1 million? Well, that's a whole other problem. Not right now. All right. Boy, that was so apropos. So writing code that works and is correct is the most important thing, all right? Your boss is not going to like you if you have well-designed code that doesn't work. You can't ship broken code. You can ship poorly designed code that works, and then you can update it. So yeah, correctness is the most important thing. Of course, once you have correctness down, once you have working code down, then you start thinking about, okay, how can I make this well-designed? So yeah, correctness should be verified using tests. I remember being in university and writing these and being like, okay, it ran once, it ran twice, that's good. It should work all the time, but it becomes a very different thing when you're writing code for thousands of people. If you're writing code for hundreds, well, I write code for hundreds, I guess, my tests. And so when I'm writing it, I'm very, very aware that 100 people or 200 people are going to be testing this out and finding all the mistakes. So when I write tests, some of them are a little haphazard, but I'm very, very aware that, okay, I'm being held to a higher standard now. All the tests that I use to test your code are tests that I use to test my solutions, right? So yes, make sure it works. And once we've done all that, once we've made sure that it runs and it's correct, we should start thinking about other aspects of design. Right, so once we lay the foundation, if you're building a house, once you build the foundation, once you put up the walls, then maybe you start thinking about how you're going to decorate it, how you're going to, where you're going to put the couch, where you're going to put the kitchen table, etc. So yeah, Now we want to make it nice. We want to make it so other people feel comfortable using it. Yeah, we want to make something that's easy to update. And yeah, essentially, once you stop updating your code, you could find a lot of broken code on the internet. You know, you come to a website, it says, oh yeah, this code does this and that, but it hasn't been maintained for the last 2 years. Well, it's a gamble whether or not that's going to work. All right. So design, when we're talking about design, there's low-level design, which is I'm making my low-level objects. Once I've decided what objects I need, I want to, choose what objects I want to use. I want to protect my objects, so C++ and other languages in general. So those access modifiers, things like const, you don't need them, right? You can write code without them, and it'll work just fine. It's all there so that the compiler tells you when there's a mistake. That's it. And well, it also prevents other people from misusing their code, because their code won't compile if they try and do something they're not supposed to. So I suppose it does a little more than just catch your mistakes. It also protects it, but yeah. All of those things we do are so that the compiler catches errors before the real world catches them. And keeping interfaces abstract, you don't want a really complicated interface to your class. You want something simple that people know how to use. You want to hide as many details away because you don't want them making decisions that you should be making, right? You should understand the complexity and then present it simply. So yeah. And then high-level design. Well, you think about, there's what's called architecture styles, which maybe are a good starting point. Develop an effective workflow. So we'll talk a little bit about some common ones. Refactoring. Again, this is something I want to, we're going to see it a little bit later on. It's something I want to talk about more as this curriculum evolves, because it is really important. Refactoring is when your code reaches a certain size or you're encountering a problem that you want solved, then you're going to change your code, not so that it works differently, but so that it's designed differently. And that'll help you solve problems such as updating or whatever. And separating objects into logical categories. Again, a lot of these are heuristics, right? They're not laws, they're not rules. They're things that tend to work well. So sometimes there's always exceptions where they don't. All right, so low-level design, you should start thinking about when you're making an application, what objects do you need? What data do they contain and what behavior do they need? And then you can start thinking about how they're going to interact. Can you reuse existing classes? That's important because existing classes have been tested, they've been used by people, bugs have been found, they've been optimized. What do your classes have in common with each other? So classes that have a lot of things in common are going to be working together. And what information should be exposed and what information should be hidden. So these are all considerations at low level. Yeah, we'll talk about this and then we'll head off for the day. So classes should be simple. They should have a single responsibility, same as functions. You don't want a big class that does a lot of things. You know, our game trucks class, even though it sort of handles everything, its responsibilities are simple. And when it has to pass responsibilities off to another class, it does that. So yeah, your classes should have a narrow scope. Encapsulation is the art of hiding unnecessary details. And this is a lot of implications, more than you would think. You don't want to expose unnecessary details because they can be misused. Yeah. Limit the ways other people can use your class, and this helps the compiler catch errors. And you know, the principle of least privilege is sort of related to that. Only allow access to what is absolutely necessary. I'll leave you with this story. I don't know if you guys were here a few years ago when Carlton actually got hacked. So CU Learn was hacked, or not even CU Learn, but I think the entire system. And they demanded money. So this idea of hiding details that you don't need to expose is actually applicable. It's very real. So I don't know I think what they said happened was they closed the security breach and then they reloaded from a backup. Maybe they paid them. I don't know what happened, but yeah. So we'll continue this. Get your assignments in this weekend and have a good weekend, and see you guys next week.